A very good morning to friends of class 12th. Today we are going to start with unit number 3, that is magnetism. After covering the topics of electrostatics, that is unit 1, and current electricity, that is unit 2. Now this is the third unit, and this unit is about magnetic properties of material and magnetism. Okay. The full name of the unit is Magnetic Properties of Materials and Magnetism. We first start this chapter by studying this topic, magnetic effects of current. That means what exactly is magnetism, that we will discuss in the later chapter. But first we have to understand what are the magnetic effects of current. See, current has got many effects. Current has got heating effects. Current has got charging effects. And one of those effects of current is the magnetic effects. Wherever there will be electric current, I am talking about DC current. Okay? Wherever there will be electric current, there will be a magnetic field around it. Now, if there is current, there is magnetic field. Is it always true? No. If the current is DC current, direct current, then only it gives magnetic effects. AC current does not have any magnetic effects. There are reasons for it. So when I am talking about magnetic effects of current, I am talking about only the DC current. It is not AC current, it is the DC current. Okay. Now, the first thing that comes into mind, that what is this magnetic field? You have learned about electric field, you have learned about how to calculate electric field and how to calculate electric force. This time, we will start this topic by calculating the magnetic field. Okay? Without going into the deep of what exactly is magnetic field, it is you can say similar to electric field, but how to calculate the magnetic field, how to bring out the numerical value of magnetic field. See, there are two laws which can help you to calculate the magnetic field. One of the law is this biot law, but it is not pronounced as biot. Actually, the T over here and the T over here, this is silent. So we basically pronounce it as savarts law. Okay. Now what is savarts law? Savarts law will tell you the magnitude of magnetic field. That how much the magnetic field is. Is it very high magnetic field? Is it very low magnetic field? So how do we represent magnetic field? We represent magnetic field by the letter B. B, just like capital E, shows electric field. Capital letter B shows magnetic field. Okay. Now, in this law, you can see that this magnetic field is not calculated over here. What we are calculating? Do you know what is this D? This is the differential wala D. Okay, that means we are not calculating the total magnetic field, we are simply calculating a small part of this magnetic field. Okay, the law is not complete. It does not give the full information of magnetic field, it gives only a small portion of this magnetic field. Now, on what factors does this magnetic field depends upon? This, on the other side you can see, what it is? It is IDL sin theta divided by r square. Okay? That means the magnetic field which we have depends on what factors? First of all, it depends on current I. It is directly proportional to I. Means if you increase current, magnetic field increases. If you decrease current, magnetic field decreases. It depends upon dl. What is dl? L means length and D means small part of the length. In the nearby diagram you can see that there is this is what? This is a current carrying wire, and I have chosen a small part in this current carrying wire from here to here. It's a small portion, so instead of calling it L, I will be calling it as DL. Okay, so magnetic field depends on length of the wire. If I reduce this DL, magnetic field becomes less. If I increase this DL, magnetic field becomes more. So I and DL. It is again inversely proportional to square of distance. Gravitational force similar to this, electrostatic force again similar to this. So this is basically also what? An inverse square law. Inverse square law. Okay. So current, length, distance. Where is this R? Suppose for this current carrying wire, I am interested to find the magnetic field at this point. This point. Okay. Then R will be the distance between that point of concern and the center of the earth. Okay. Can you see in the diagram? This R is the distance between the point where I have to find the magnetic field and the center portion, the center part of the length dl. You have to connect by drawing a straight line, point, midpoint, and this distance will be R. Now coming to this factor sin theta. All the laws that you have learned previously does not involve sin theta, cos theta, tan theta. That means gravitational force or electrostatic force, they actually do not depend upon angles, but magnetic field depends upon the angles. Now how do we see this angle? Okay, sin theta we know how to calculate, but how to find this theta? You have drawn this R. Okay, now take two directions. This will be the direction of electric current, and this is R. R is actually a vector quantity. Here is the tail and this is the head. R is a vector having tail and this is the head. So consider two directions, direction of current and direction of R. Okay, now the angle between these two directions will become your theta. So magnetic field has angular dependence theta. Where is this theta? The theta is this. Clear? So this makes Biot-Savarts law different from other laws, that Biot-Savarts law depends on angles, whereas electrostatic force or gravitational force, they do not have any angular dependence. This is the law. Magnetic field at a point is directly proportional to current, directly proportional to the length of the wire, then it is inversely proportional to square of distance, and again it is directly proportional to sin theta. Okay? Now, if I remove this proportionality sign, I will have some constant over here. Can you see this? This is the constant. What is this constant? This is mu naught upon 4 pi. Mu naught upon 4 pi. You already know why this factor 4 pi comes over here, because of the three-dimensional nature of magnetic field. Because electric field is also having three-dimensional nature. So we write 1 upon 4 pi epsilon 0. You remember? Yes. So for the same reason, we write 4 pi in the denominator. And now coming to this mu 0. See, in electrostatics, we used to have one more constant, that was 1 upon 4 pi epsilon 0. Okay, 4 pi is due to the 3D nature. Epsilon 0 is what? It was the permittivity of free space. Permittivity of free space. Okay, what does this permittivity measure? This permittivity measures the inverse degree of freedom. That means if a medium allows the charges to interact, this will be less. If it does not allow, this will be more. But here we are writing mu 0. Mu 0 is what? It is the permeability of free space. Minus what? Permeability. It is different from permittivity. Okay. And what is permeability? Permeability is the direct degree of consent given by the medium for magnetic field to exist. Okay, यानी कोई भी मीडियम जो है अपने अंदर अगर मैग्नेटिक फील्ड को एग्जिस्ट होने देता है तो म्यू जीरो की वैल्यू ज्यादा होगी. If it does not allow or if it restricts the magnetic field in itself, then the value of mu zero will be less. ठीक है, तो mu zero क्या है? इनवर्स डिग्री है या डायरेक्ट डिग्री है? डायरेक्ट है. It is direct. Clear? More of the magnetic field exists in the matter, more will be the value of mu zero. So we are writing in the numerator. Remember that epsilon zero was written in the denominator. Okay, so removing this proportionality sign, putting a constant. Now this constant again has a particular value. This is simple value mu 0 upon 4 pi is equals to 10 to the power minus 7. Okay, it has got some unit also. That unit we will discuss later on. But this is the numerical value of mu 0 by 4 pi is 10 to the power minus 7. Got this? This is the rough bioscience law. Now we come to the second part, explanation, the diagrammatical explanation of Bioscience law. You see this? Okay, what's this? This is a current carrying wire. What is this? dl, the length due to which I am finding the magnetic field at this point. P. What is the name of magnetic field? It is dB. Oh my God, I have written a vector over dB. That means magnetic field B or dB is what? It is a vector quantity. It is having magnitude. It is having direction, and it is following the rules of vector algebra. All the three things. So dB is again what? It is a vector quantity. Okay. I is what? The current flowing in this wire. dl is what? It is the length of this wire which I am considering. See, when I am calculating this, the reason is this, and I am not considering this part of the wire or this part of the wire. These portions are not existing. मैं उनको neglect करके दे रहा हूँ. ठीक है, वो neglect हो गए. सिर्फ इसकी वजह से जो magnetic field होगी यदि वो find होगी. ठीक है, बाकी वायर को भूल जाओगे. अच्छा, what is the current flowing in this? The current flowing in this is I. So जब आप इन दोनों को multiply करते हो, current into length, उसको क्या बोलते हैं? उसको बोलते हैं करंट एलिमेंट. क्या बोलते हैं? करंट एलिमेंट. देखो यहां से लेके यहां तक. What was that? That was a total current. But what is this small portion? This small portion is now known as the current element. Okay? Got it? This is Bioscience law. But this is only the mathematics of Bioscience law. अभी आप बोलोगे सर dB का डायरेक्शन है ना? वेक्टर क्वांटिटी लगाया ना? dl का भी डायरेक्शन है ना? वेक्टर क्वांटिटी लगाया ना? तो इनके डायरेक्शंस क्या हैं? See, dl का डायरेक्शन वही होगा जो करंट का डायरेक्शन होगा. Whatever is the direction of current, the same is the direction of current element IDL. So we can also put a vector sign over this dl. Don't put the vector sign over I because I is current and you know that current is not a vector quantity. So what is this? Sorry. This is what? Current element. It's a vector? Yes. What's direction? Direction of current is direction of current element. Now what is direction of magnetic field? Magnetic field, oh my God, I have to learn one more law. The right hand rule to find the direction of dB. To find the direction of magnetic field. How to find it? See, right hand rule, very simple. Very simple. What you have to do? Take your right hand and put your right hand in the direction of current. Put your right hand in the direction of thumb of right hand in the direction of current, and you just have to fold the fingers. Okay, where is point P? Point P is on this side. So when I move my fingers this side, my fingers are pointing inward direction. So the direction of dB is inside. Okay, now if I reverse the direction of current, current कैसे जा रहा है? अभी suppose current अगर उल्टा जाता है, if the current reverses this direction, then this will be direction of current. The point P is over there. So when I move my fingers, the fingers show the outward direction. So the direction of magnetic field will be also outwards, like in this diagram. Okay. So whenever you are finding magnetic field, you have to find its magnitude plus you have to use the right hand rule to find the direction of that magnetic field. Okay. So this was the basic of Bioscience Law. Now the thing comes that if magnetic field is a vector quantity, do we have a vector form of Bioscience Law also? Yes, we have a vector form of Bioscience Law. See, vector form of gravitational force was not that important. Vector form of Coulomb's law was also not that important because these were not having angular dependence. They were not depending upon angles. But the vector form of Bioscience Law now becomes important because dB depends on angle also. What does it depend on? Angle. Yes, because it depends upon angle, you have to learn the vector form also. Okay. Now, if you are using the scalar form, the previous form, you have to do two things. Ideal sine theta upon r square plus right hand rule. Here, in the vector form, right hand rule is not required. What is required is this. See, nothing is changed. dB, vector dB is equals to mu 0 upon 4 pi, pehle likha. I, pehle likha. R square, pehle likha. The difference is dl cross r. It's not r actually, it is r cap. What is r cap? R cap is a unit vector. You know, whenever you put cap, it becomes a unit vector. The magnitude is 1. So when I am multiplying this with r, the magnitude is not changing. Why not changing? Because this is unit vector multiplying with 1. Okay, but where is this unit vector? This is the unit vector r cap. This is unit vector r cap. Okay, so now when I do this operation, do you know vector product, okay, dl cross r, how do you find? See, you are multiplying two vector quantities. This is first, this is second, and then you find the directions. Using these two, you get the direction of dB. So how to find it? First, I dl, what is the direction of dl? This. So keep the fingers in the direction of dl. Then move your fingers towards the direction of r. Close the fingers towards the direction of r. So this is dl. Where is r? R there. Okay. So close the fingers, make a fist r and a thumb. Thumb will tell you the direction. What is the direction? It is inside. Got it? So what is the direction of magnetic field? It is inside. So if you use right hand rule, again the direction is inside. If you use the vector product rule, again the direction is inside. But it is not sufficient that you learn both the laws to find the directions, because sometimes this will be useful, sometimes that will be useful. RH rule, good. Vector product rule, better. Sometimes you will be confused in using RH rule. So at that time, you can use this. Okay, so this makes the complete law. Bioscience law dB, vector dB is equals to mu 0 by 4 pi I dl cross r over r. Okay, now we take a small question. You can see this is x-axis marked in meters, this is y-axis marked in meters, and there is a small current element at the origin. Small. And there is some current flowing in like this. Okay, so first open up the data. Suppose the length is 0.1 meter. Suppose the distance, okay, at this point you have to find the magnetic field. At this point, what are the coordinates of this point? 0, 1. It's in meters. So what is this distance? This distance is what? 1 meter. So R becomes 1 meter. What's the current given to you? Current given to you is 2 ampere. How to find the magnetic field at this point due to this current element? Very quick. So what is it? Use the law. dB equals to mu 0 by 4 pi. Ideal sine theta over r square. Now put the values. Mu 0 by 4 pi. Remember the value. Value 10 to the power minus 7. Current. What is current? It is 2. What is dl? dl is 0.1. What is theta? See from the diagram what is theta. Current is going in positive x direction. Now where is this r? See. To draw r, you have to join this line. This is r. And what is the angle between direction of current and direction of r? It is 30. No, 45. No. You can see it is how much? 90 degrees. Okay. What is sine 90? You already know sine 90. Okay. So just put these values. Current, dl, R. What is the distance? Distance is 1 meter. So you put 1 square. Sin theta equals to 90. So sin theta, 90 sin 90 equals to 1. Put this, and there you have this value 2 into 10 to the power minus 8 Tesla. What is it? Tesla. What is Tesla? Tesla is the unit of magnetic field. What is it? Tesla is the unit of magnetic field. Okay. For different purposes, we use different units for magnetic field. We use Tesla sometimes Gauss. So this is how we use Bioscience law to calculate the magnetic field, and now the direction of magnetic field due to this current element at this point. How to solve? Right hand rule. Direction of current. Thumb. Point is where upwards. When you bring the fingers upwards, it shows outward direction. What is the direction of this TB? Outwards. The dot. Circle over it. This shows outward direction. Okay, now you can see the magnitude of this magnetic field 2 into 10 to the power minus 8. It's not less, it's very less. So if you calculate the magnetic fields like this, the numbers that you get is very less. This small magnetic field is not able to influence any of the magnetic equipments. So what is the problem over here? It is so small that this cannot be detected, and for this purpose Bioscience law cannot be experimentally verified. You can experimentally verify Coulomb's law, universal law of gravitation, but this law is a bit difficult to verify, and now you know why. Because magnetic field is so small that it cannot be detected by any of the magnetic instruments.